In this video we're going to consider the concept of an inverse transformation and how we can model those using matrices. So an inverse transformation is really one that just reverses or inverses the effects of a transformation. So if we had A being a matrix which represents a transformation which maps all points x, y to their image points x dash y dash, then the inverse transformation would be the one that takes them all back to where they started. So then A inverse represents the inverse transformation which maps all x dash y dash back to their original points. And what that statement there is saying is that in fact if we have a matrix for the original transformation, then it's the inverse of that matrix which will perform the inverse transformation. So let's just think about that maybe algebraically for a moment and see why that's the case. So we're saying if we can get all image points x dash y dash by multiplying the matrix A by all the coordinate points x, y, so A is producing the transformation which takes x, y to x dash y dash, then we could multiply by the inverse on both sides. So pre-multiply by the inverse, which on this side would just produce I times xy, which is equal to xy. So in other words, if we just sort of reverse the order of that statement, then we're saying the points x, y can be found by multiplying the inverse of A by the image points x dash y dash. Now this is going to be quite useful to us in sort of coming concepts in coming lessons, but let's just at the moment think about what that means. Now for some transformations, in fact, the inverse transformation is the same as the original transformation, isn't it? So you think about something like reflecting a point, that's my point, and I reflect it in any line, let's say just reflect it in the x-axis, there's P dash. Now what's the reflection that's going to take P dash back to P? Well, it's exactly the same transformation again, isn't it? It's reflection in the x-axis. So let's consider reflection in the x-axis. So I'd say the matrix that produces that, well, we know that point 1, 0 doesn't change. The point 0, 1 goes to 0, negative 1. So that was our matrix for transformation, or reflection rather, in the x-axis. Then A inverse, whoops, don't do that one just yet. A inverse is equal to 1 over the determinant, which in this case is going to be negative 1 minus 0 times 1, 0, 0, negative 1. That's going to be equal to negative 1 times 1, 0, 0, negative 1. So let's and when we multiply that, in fact the thing that I didn't do in that first step was to switch my A and D around, did I? So I should have switched my A and D around, which would have made this one negative 1 and that positive 1. And so when I multiply those, I end up with, can I sneak this in down here? I end up with 1, 0, 0, negative 1, which is exactly the same transformation matrix that I started with. And so just showing the idea that some transformations and their inverses are identical. Alright, let's consider then maybe just a couple of examples where we might sort of use this. And like I say, we'll go on to other cases where it's a little bit more useful than just in an abstract sense like this. So let's say let T be a transformation matrix. Let's just go 1, -3, -1, 4. Then T inverse would be 1 over, what's that, 1 times 4 is 4, minus 3. Swap those ones around, take the negative of these ones. And 1 over 4 minus 3 is just 1 over 1. So 4, 3, 1, 1. So those two matrices, T and T inverse there, will produce the inverse transformations of each other, or the second matrix will bring all the points back to their original places. What about if we had a second example where we said find the inverse transformation of that represented by, and let's say we had the point xy being taken to the point 2x minus 5y and negative x plus 2y. Alright, so we've got a transformation represented by that. What is our rule for our inverse transformation? Well, first of all, let's remember that we can put that matrix algebra. So we're saying the image point is 2 times, or the x-coordinate of the image point is 2 times the original x-coordinate minus 5 times the original y-coordinate. So we can use 2 and negative 5 as the first row of our matrix there, and then negative 1 and positive 2. So that's just using those as the rows of our transformation matrix. Then we can find the inverse transformation matrix by taking the inverse of T. So what's that? 1 over 2 times 2 is 4 minus 5. Swap around the A and the D. Take the negative of the B and the C. So that's going to be 1 over negative 1, so basically everything in here is going to get multiplied by negative 1. So that's the inverse transformation matrix, and so we could write our rule like we did, like the question was phrased. So we could say the rule for the inverse transformation is this one. We start with a point, and reading along the first row of that matrix, it's negative 2x minus 5y, and then negative x minus 2y. If you wanted to sort of check that that indeed works, just go up to the first part here, take a particular xy coordinate, and apply this rule to it here, and then the results of that take and input down into this rule here. So in other words, input into those equations there, and you should see that we end up back at the original xy coordinate that we started with. Alright, so that's a bit of an introduction there to inverse transformations. Like I say, we'll use those in other ways as well.